Hi, my name is Johnny Scott, and I will be presenting with Joseph Douglas. Today, we were
Hello.
supposed to have um, Jared Homashak or Mr. Homashak with us, but he was unable to make this presentation. So we hope that everything's going okay with him and that he's doing all right. So it will just be us two going over different things from the semesters and the different things that we have gone over and presented to you. And with me and my presentation, I will be going over different statistics and probability, like different ways to find those and whatnot. And this will be my semester in review. And then once I'm done, Mr. Joseph, we will start going over his, and we each have gathered questions that we would like to ask the other person because we honestly kind of just want to clarify everything that we've gone over. We're going to kind of just hit things here and there. We're not going to go over every little thing that we did, but we will just be hitting different spots of the semester just to kind of clarify things that we may have been confused about.
Okay. Johnny Scott, my first question for you is what is a Venn diagram?
Now, as you've already seen, Joseph is curious as to what a Venn diagram is. And I went over this in my first presentation. A Venn diagram is a set of different circles. Each circle is representing something different, and the circles will correspond with one another and they will overlap. Venn diagram is used to help you keep data and to kind of compare different things. The overlapping parts of the circle is kind of where they kind of compare or whatnot. That's where the things will come together. The overlapping um, parts are what falls in more than one category. And the middle is where all the circles kind of come together, and there will be something from every circle in there that goes into each of the different circles. And it's this is just breaking up the different data that you have. And um, as you can see over here, we have three different circles. We have circle A, circle B, and C. And as you can see over here, this is where they start to overlap. In the brown part, you have A and B, and the only parts that overlap in A and B is circle A and circle B. That's why the brown part is called A and B. And as you can see in the red part and the green part, it does the same thing. So we are fine with that. And then in the very middle, which is kind of the tan part, it has A, B, and C. And it's labeled A, B, and C because there is something from all three circles in this one spot. And I hope that that kind of helped you see what a Venn diagram kind of looks like. And if you were to label these, anything that falls in both A and B category right here, it would just be put into this one area right here. So that is generally what a Venn diagram is.
Okay. Thank you. My second question, Johnny Scott, is what is an intersection and union of a Venn diagram?
Awesome. So the intersection of a Venn diagram is the area that covers that multiple spots overlap. The intersection is compiled of more than one. As you can see down here,
I'm
the
sorry, that's my
intersection,
cat.
as you can see, the intersection down here shows you that it has two different circles, but the intersection of the two circles is the middle. We are not counting the two separate circles. We're only counting the part that's the same with the two circles. Now, the union are kind of the circles in general. And I went over this, kind of looked at it and everything like that. These are the circles just in general. The union would be noted like this. It'd be A with kind of a U shape right there, and B, which is two different circles is A and B. And the intersection would be noted with an A and kind of like a upside down capital U and B. But the union is everything in the circles. The intersection is what these circles have in common. And the only reason this whole union is highlighted is because the things in the middle, they kind of go in both different circles. So you have to include this because if you don't include the what they have in common, then you'll be missing stuff from A and B. So you have to include everything. It's just generally everything included once. That is the union. And the intersection, again, is just what they have in common.
Okay, thank you, Johnny Scott. So my third question is, what is a frequency table?
Awesome. A frequency table. This is something that shows you visually how many times an event happens, and it's showing it on a table. This table is broken up into two different pieces. And as you can see right here, we have the frequency and we have the marks. And the way that I would describe a frequency table is it's pretty much a fancy t-shirt. Fancy t-shirt, that's it. On the left side, it's composed of the ranges of data. And then on the right, it's composed of how many times something occurs in the range of data. And this is honestly what it looks like. And class marks, this is like kind of how many marks the class have made. And you have 11 through 15 in the first one. And then only the mini marks, it occurs two times, 11 to 15, which would be 11, 12, 13, 14, 15. That only happens twice. And as you can see, you can come down here, go all the way through the whole thing. Like right here, you have 31 to 35. 6 marks in that range. So this is what a frequency table is. Frequency table generally just goes over a range of numbers and how many times in that range something occurs.
Okay. So my fourth question is, come on, buddy, over there. My fourth question is, how would you contrast and compare a bar graph and a histogram?
Awesome. Well, a bar graph, this is used to show single events. Different events like different grade levels, and with a bar graph, the bars do not touch at all. The number of certain categories, these bars, again, they don't touch. But over with the histogram, these bars do touch. There's no spaces between the bars. This is generally, this is used for a range of data. Like a histogram can be made up from a frequency table. And then these will generally be presented with numbers. And then back over to the bar graph, just to kind of make sure that y'all understood what I was talking about. With single events, it's kind of like we have like cat, dog, spider, things like that. Like how many cats are in this place? How many dogs are in this place? Like if you have the animal shelter, I would have like a cat, dog, rabbit, things like that. And then with a bar graph, you would just put how many of each animal you have. That's what I mean by showing a single event. And grade levels is like just an example of like first grade, second grade, third grade, different things like that. But with a histogram, I would be like in a whole school, like let's say a whole school district, how many kids are from ages 0 to 5, and then from 6 to 10, and then from 11 to 14. That's generally how I would use a histogram. Now, will it always be used that way? No, not always. But that's just a general rule for it. Now, you should note that both of these are used to represent data and to compare them. Compare data and represent data. They're generally used for different kinds of data, though. That's the difference.
And how is a histogram related to a bell-shaped curve?
Awesome. And this is a histogram and bell-shaped curve. As you can see, these kind of correspond with one another. And I know this little picture thing's kind of getting in the way. I'm sorry about that. But I just want to kind of move it to where y'all can generally see everything and kind of look at this on your own. So a histogram and a bell-shaped curve. Bell-shaped curve, as you can see right here, it starts low on the left side. And then its peak or its high point, its peak or its high point is right in the middle. and it goes back down on the opposite side. Now, both of these kind of use bars to represent their data. So as you can see with the bell-shaped curve, there's bars in the middle. Even though they're curved, it's still kind of derived from bars. And simply how I would compare these two is, like I told you earlier, how they kind of go up in the middle and then on the sides they kind of go down. But after you, like you can see right here, this will be further explained a little bit later on. But if I were to put an arc over this, then you would be able to see the bell-shaped curve, which is, I mean, that's what this is up here, a bell-shaped curve, because it's shaped like a bell. Now, if you want to go ahead and read this, you can. I'll go ahead and do that for you. Both of these use bars to represent their data. A bell-shaped curve has a curve at its highest point on the graph. Simply how I'd compare these two is when you create a histogram, it is the backdrop for a bell-shaped curve. After you have a histogram, you simply create a curve from the x-axis and the y-axis. Curve it to the highest point of the graph. At the same rate, it will drop on the other side.
Okay.
And yeah.
Okay. I am unable to clearly see what question 6 is. Should I move on to my 7th question?
So, based on what you know, how could you explain a skew line? And that's kind of what question 6 is. It's just explaining a skew line.
Well, what is a skew line, though?
Well, good question. So skew line is from a bell-shaped curve. And as you can see over here, skewed lines. Generally with a bell-shaped curve, a normal one, as you can see right in the middle, the highest portion will be the mean, median, and the mode in a regular one. But as you kind of skew it, which over here I have them out for you, skewed left, this one is normal distribution right here, normal line. And then skewed right should be all the way over here. So I have, the mode will always be the highest point, okay? So whichever direction kind of drops the most would be the direction that it's skewed in. So over here, you see how this kind of goes left a lot more than the right side does. The right side just boom, plummets. But then the left side kind of has a nice little slope to it, kind of like a slide, as when we were a kid. So if you can also say, whichever way it slides is the direction that the skew is. So this one slides to the left. So this one is skewed left. This one over here slides to the right. So it's skewed to the right. This one is just normal. It's not skewed left, nor is it skewed right.
Okay, thank you. My next question is, what is central tendency?
So a central tendency is a single value that attempts to describe a set of data by identifying the central position within the set of data.
Okay. So like mean, median, and mode.
Yes, those are single events that you try to show different people or whoever's kind of looking at the data. Those are single things, different things that you're trying to show them what they are in the data.
Okay. And my final question, Johnny Scott, is what elements, whether mean, median, or mode, would change if you added an outlier number to the data?
Okay. Well, first we kind of want to know what mean, median, and mode is. The mean is the average of all the data. The median is the middle number of all the data. And the mode is simply the number that appears most frequently in a set of data. So to kind of see and show what would change, we've seen this before, but I'm going to show you again kind of how these would change. So I had these numbers up here, went ahead, did them previously. There are 40 numbers total. And this is the mean without the outlier, without adding a different number. These are just straight 40, just 40 numbers across the board, okay? So right here is the mean. If you add all these numbers up, divided by 40, you'll get 75.1. Then if you want to find the mean, just that means the middle number of the set of data. The mean is 78. And the mode, which is the number that appears most, is 75. Now, if you come up here, you can see I added an outlier. And this is with the outlier 25 added. The mean would then change to 74.46. The median, since there's more number added, it would change. The number is lower that was added, so the median is going to be a little bit lower. The mean is now 76. The mode will stay the same because it's the number that appears most. The mode will remain at 75. And also what's kind of cool is you can kind of see a bell-shaped curve if you use your imagination. You can see I have 5 different marks, right? 5 different segments in my frequency table right here. And if you were to make it into a histogram, you could see that this number is really low. And then it goes to the middle, which is right here. This is the middle category. 13 is the highest. And then it drops back down to 6. So this is your peak. And it kind of, right here, which you watch the mouse, it goes up, boom, right there to the peak, and then it just drops down. And then that's all the questions that I've had that Mr. Douglas and Mr. Jarrett have kind of like wanted to know over the semester. So now we're going to go and we're going to ask Mr. Douglas different questions and have him kind of explain things to us. And hopefully they will become more clear to me as well as more clear to you.
Excellent. Thank you for this information. Should I go ahead and bring it up?
Yes.
Okay. Here we go. So I also have 6 questions. Let me just put this in slideshow mode, and you have your questions, right, Johnny Scott?
Yes.
Okay, so let me just get to slideshow mode. Here we go.
So can you explain to me how to find the different angle measures on this complex figure?
Well, that's an excellent question. So the first thing we need to look at is the angle measures we have, which in this case, here we go. In this case are 63 and 61. The total measure of any angles within a triangle will be 180. So to find the measure of angle 7, we can simply add 63 plus 61 to 124. Subtract that from 180 to get 56. Therefore, angle 7 has to equal 56. And then from there, we can see that it's diagonal to angle 12, which must also be 56. And from there, we can use rules of like complementary and supplementary angles, subtracting from 180 to find all the rest of these angle measures. So, and then finally to list the similar angles, as we can see, angles 1 and 5 are similar because they're diagonal from one another. Angle 2 and the angle labeled as 63 are also similar, which means angle 2 is equal to 63 degrees because it's diagonal, basically the diagonal angles. And then for supplementary, it's if this angle plus another will give us 180. So angle 6 is supplementary to 61, which means angle 6 has to be equal to 119 degrees. That's basically it for number 1.
So my second question is, how do you find the lines that are tangent to x at 0 and y at -9, and then x at 0 and y at +9?
Okay, so if we're finding angles that are tangent to a circle, the first thing we need to do is take a look at the circle. So this circle has been plotted with the points -9, 0, 0, 9, 9, 0, and 0, negative 9. Those are all along the edge of the circle. So the tangent lines are ones that run through a point on this edge of the edge of the circle. So in this case, let's just say we take 0 and 9 and 0 and negative 9 and put lines of tangency through here. As we can see, both of these orange lines are parallel to one another. Therefore, what we can conclude from this is that two lines that are tangent to one another touching the edge of a circle will always be parallel to one another. Right?
Okay, so can you tell me what tangent is real quick?
Okay, tangent is across from, or so like, you're familiar with trigonometry, right?
Mm-hmm.
So like sine, cosine, and tangent.
Yeah.
Tangent is opposite divided by adjacent, or opposite from adjacent. That's really what it has to do with, is like if it's from the opposite side, or directly, like going directly across but through a certain point.
Okay.
So not exactly like perpendicular. It usually involves an actual shape.
Okay. So these two figures that we have right here, how do you get from the figure on the left to the figure on the right?
Okay. So the figure on the left, it has been rotated 180 degrees, because as we can see here, this, when it's on the top, this green triangle to the right here is on the upper right side, but then it's on the bottom left.
Mm-hmm.
The problem is, this problem asked us to, if you see this baby blue line right here, to reflect this on the left over this line.
Mm-hmm.
So what we instead needed to, so if we were to do that, the question says, would it look the same as rotating at 180 degrees? Well, the answer is no. And this is what it would look like if it were reflected, because the green things would stay on the same side if you were to reflect it vertically over this blue line. And it would look like this.
Okay, I got you. So it just wouldn't look the same if you reflected it, so you had to rotate it.
Yeah, so the answer is no. Rotating this shape 180 degrees does not give us the same result, because this is not the same as this.
Okay.
Okay.
So why is triangle QPT the same as triangle SPT?
Well, the simplest answer for that is that they both follow, is that PT is a line of symmetry. So as we can see, both of these triangles, they share the same line. PT is one line. So we know at least one of their sides is the same. But then we also can see that these two blue lines are labeled with one mark to show that they're similar to one another.
Mm-hmm.
And finally, QT and ST are marked in red with 2. So using based on the side rule, that means these two triangles are the same or similar.
Oh, got you. So then why is QPT, the angle QPT, the same as the angle SPT?
That's a good question too. It's as we already said, lines QP and PS are marked as similar, and then also PT is similar, so that if these two lines that an angle forms between are the same, then that angle must be the same.
Okay. And then, so for the first one up there, it would kind of be, for the first like triangle QPT and SPT, the explanation for that one would kind of be the same as why triangle QPV
Essentially,
is the same as SP.
essentially.
Okay. And then why is angle QVP a right angle?
Okay, so angle QVP has to be a right angle because lines PT and line M, if you can see that's what this is labeled, are perpendicular to one another. But even though it's not marked, the reason we know it's perpendicular is once again because of lines QP and SP, because they're marked as the same and they touch the same, they start at the same point, and then they're the same length and sloping at the same rate. They'd have to touch the same but opposite points.
Okay.
So that proves that for that to happen and them to be the same, lines PT and line M would have to be perpendicular to one another. So that in turn means that angle QVP has to be a right angle.
Okay, got you. Well, I have another question. Each shape, how do you find the surface area?
Okay, that's a good question. It depends. The short answer is for both of these prisms, it depends on which one. So we'll start with the first one. So for the first one, we need to find the surface area of the trapezoids first. Or, well, no, the surface area of this whole thing, rather, is going to be 2 times the area of the base plus the perimeter times the height. That's the basic prism formula. To find the area of the base, we need to take 1/2 times A plus B, meaning the length of these two sides, 17 plus 26, and multiply that by the height. So we can start by taking 26 plus 17 times 1/2 times 12, which gives us 258, which means the area of this trapezoid that forms the base of the prism is 258 centimeters squared. So then if we plug that back into this, which is 2 base, so 258 times 2, plus our perimeter, which if we add 12 plus 17 plus 15 plus 26 is 70, and then we multiply that perimeter by 4, which is our height, then that will give us a total of 796 centimeters as our surface area. Now for number B. This is very similar. The surface area is 2B plus perimeter times the height for every prism. But in this case, to find the base, since it's a triangle, we need to take 1/2 the base times the height. So 1/2 times the base here is 15, and the height, since this is a right triangle, this wouldn't be the case if it wasn't, but since it is, this here is this 8 meters is the same as the height. So 15 times 8. You got the idea, right?
Yes, I did.
15 times 8 times 1/2, that would give us the base. Then we just multiply that again by 2 plus perimeter times the height. That's always the formula for the prism. The only thing that changes with the surface area of a prism is how you're going to find the area of the base itself.
Okay. For my last one, can you tell me what a vertex figure is? Or explain to me what that is.
Okay, so a vertex figure has to do with tiling, and in this case, it's a figure that's made up of other figures in which there's no overlap. So think about a brick wall. You know how like you'll have 2 bricks stacked on top of one another, and then where those 2 touch will line up vertically with the middle of a brick above it?
Uh-huh.
That's not the case if it's a vertex figure. So bricks are not vertex figures. So here, each of these sides on this shape are the same. They're shared. So are all the vertices. So that would have to mean this shape here is a vertex figure.
Okay.
And looks like that's it for mine.
Okay, well, thank you guys for listening to a review of the semester and kind of what we've both have gone over. I hope that you guys have learned something and have enjoyed this meeting with us. Thank you very much for listening and giving us your time.